So it sounds somewhat obnoxious, but I thought I would talk about, I thought I'd go ahead and put the word modern as well as the word convergence in a talk presentation. If we look at this, for me, I'll turn this on and then it'll work. For me, there we go. I remember it's a puppy picture. Puppies are adorable. They really are. So I started out oddly enough as a scientist. So I was doing, in particular, a lot of sort of early, genomics, large-scale image analysis. I remember being a young scientist and walking into really the little data center server room we had there next to sort of a big sequencer. Sitting down in front of this computer, and this little thing pops up and says, would I like to start going through the firmware upgrade process on the controller head of this little SAM that we had. And I thought, yeah, sure, why not? Click, 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 and thus began really the first time where I'd used a computer and then watched this very expensive thing that basically had like 4 or 5 years of my work on it just completely melt down and die. So for those of you that have ever said, oh, we'll fail over controller heads and we'll do a firmware upgrade and everything will be like perfectly fine, and I'll go get some coffee and I'll come back. And what actually really started was 4 days of basically, where I think the end of the 4 days was me really sort of understanding that everything was not going to be retrievable. At that point, I'd not showered for 4 days, I'd not shaved for 4 days. I was basically down to just a pair of jeans and I was sitting in my own urine. I mean, it was pretty bad. And so at that point, oddly enough, as a scientist, I sat down and I was like, well, what the f is firmware, basically? Why is it so sort of bad? And realizing, of course, that computers are pretty simple things, or they should be. I mean, you have data, in particular, when you're doing science stuff, data is the point of it. You do compute on the data and you send and receive it over a network. That's all a computer is. And in fact, scientists and accountants were sort of the original users of these magical calculators. And if you look at myself from a background, I did start as a scientist and largely sort of a system scientist. Oddly enough, my doctorate was in pathology, but I was so inspired by this sand basically on my life that I decided to go ahead and become the CTO of a system software company. And I spent a decade at Joyent largely building out what was quite an effort to finally get to the point where it was like a vendor-free experience. There was in fact nothing from a software perspective that came from anyone else in the world, and it was in fact a very liberating experience. We're also an operator, so sort of a large distributed sort of multi-continent type infrastructure, and so the system software sort of was used in earnest. And what I wanted to sort of talk about today was a couple of different sort of thoughts. And so of course one thought is we do need to actually stop piling abstractions on top of one another. So how does one within a complete system do the right thing at the right layer? And so, for example, if a file system is actually capable of caching things in memory and has an abstraction like ARC, then something like HBase that sits on Hadoop, that sits on the file system, should not have a hacked up implementation of the ARC in it. Trying to get around patents and the like. Excuse me, I'm going to cough. Well, that didn't block it at all, did it? Sorry. And so, stop piling abstractions on one another. Start having comprehensible systems. So things where you actually do something at the right layer, you have an inherit, you begin to start sort of addressing the most difficult questions that you have when you're sort of running systems, and that is, well, why is it slow? Why is it down? When's it coming back? Why? And so in fact, sort of like fault analysis and distributed applications is sort of the tough part. And you'll see these types of things where if there's a couple trends across a couple, if there's a few trends around the things that I'm talking about, it's largely how do you do things at the right layer and sort of have an inherit, How do you start having a system that can be instrumented so you know why things are slow and why something is down and when it's actually sort of coming back? And what we'll do is we'll go through really sort of 4 basic areas. So we'll say data, data centers, apps, and we'll talk about a stack. So we're going to start talking about datas, then we'll talk a little bit about data centers, a little bit about applications, and a little bit about at least the stack that we built at Joyent, so we can figure that out. Now, of course, what's in it for you? Hopefully, I just want to provide 2 simple things for you today. One is what I think is the framework for the industry. And so, you know, if we look at the world that we sort of live and work in, what our industry actually does and the point of it, and to come up with sort of a system example. And then, of course, the final goal, which was a slide I was asked to put in last night over dinner, is to actually be in a happier time full of computers and love. So I did put that in. So we're going to be in a happier time full of computers and love. And so if we start with like an example from you know, my life at one point, you take something like a typical sort of sequencing run. If you look at like a human genome, when it's all done and you're looking at it, it's about 60 gigs. But if you look at the raw data, it's typically about 2 to 4 terabytes of raw data per genome, right? And so that's basically all the sequencing runs, all the images, all the text files, sort of everything else like that. And so if you stop and you think, it means that keeping the raw data for 10 million genomes, so roughly 1 in 30 people in the United States, is 20 exabytes of data. Now, the challenge, of course, with this is that the storage industry shipped 16 exabytes of data in 2012. And so when you even start thinking about various ideas in the science world, like, hey, let's go sequence a bunch of genomes, you can, in fact, have a single idea consume an entire industry. So you could say, let's sequence everyone's genome, and what we'll do is we'll basically consume every hard drive fab forever. Okay? Now, what's really been interesting is you look at something like a Palm Treo. If you remember that magical device from 2006, a Palm Treo in 2006 had 64 megabytes in it, which was huge at the time. The 2012 iPhone 4, of course, has 64 gigabytes in it. It also has the same computational power as an iMac that you bought in 2006, and it has the same computational power as a Cray 1 that was built in 1976. Now, of course, a Cray 1, pretty badass computer, of course, at the time, 160 MIPS, 8 megs of memory, it was 5.5 tons, took about 115 kilowatts, and of course, it had you know, $30 million in today's dollars. Now, the funny part is you're working on a computer today, and sometime 35 years from now, some other asshole's going to give a slide with your computer on there and basically sit down and be like, can you believe that they spent $20 on that chip? Fools. So, but it's a pretty impressive thing. So iPhone, of course, more powerful than that. If you look at sort of like today's data center in a pretty sort of like highly industrialized build, you can, in fact, decide that you're going to do things like keep rack power relatively constant as well as cost. And so sticking things into sort of a dual 30 amp, 208 volt type, AB power, and so on like that. If we look at what's happened over the last 8 years, and I'll explain basically why, but we've been able to sort of increase either the density of CPU, DRAM, and or storage inside of basically constant rack power and relatively constant cost, where if you looked at like what we say did in 2004 versus sort of what we do today, what used to fit in 32 racks now fits in 1 rack. 10 megawatts today is 1 million CPUs, 4 petabytes of DRAM, 200 petabytes of storage, and of course by 2020 that will probably fit in around a megawatt or so. Now, of course, we do have some limits to that. Like, for example, we're going to be able to stop jamming platters into things and filling drives with helium drives, yeah, that sort of thing. Networking over the last 12 years, a lot of us forget that in 2001, when like the big .com thing was actually happening, there was in fact only 200 million people in the world that had internet access. That's all. So the whole big deal was about 200 million people clicking around basically Tamagotchi type sites on AOL or stuff like that, but there's only 200 million people doing it. Today there's 2 billion fixed line broadband users, there's 5 billion mobile internet users, and then of course by most estimates when you start looking at a lot of chips that are being shipped, which of course are still, like half the world's chips are still 8 and 16-bit chips that go in embedded systems and the like. We are in fact going to be bumping all of those up into basically 32-bit chips and then putting a little 3G or 2G chip next to it. And we're basically going to start putting everything on sort of a relatively, you know, I said enough there. I don't even know how to finish that sentence. So the key, though, is a lot of the times it's like network, compute type stuff. But the true anchor for everything, and in fact what we have as the point of it all, is data. And so I want to talk a little bit about data to make sure we understand at least like a simple, nice simple framework for data. Data has three things. It has a source, it has an observer, and it has a student, right? So basically data comes from somewhere, something observes it, something learns from it. Data only has three sources. There's only three places basically data comes from. I say that the first one, of course, is data from nature. That is the highest resolution data, so the fact that we can go ahead and have an eyeball in our head that's essentially, you know, like 4.4K in resolution, the fact that we can go ahead and have telescopes out there that can save an exabyte a day, the fact that we can't even sequence, say, more than 3% of the US population's genomes without exhausting the storage industry, nature is still the source of the highest resolution data. In fact, when I was at a pharmaceutical company in the past, at one point, we were sitting there and saying, oh my God, we're going to have to buy all this storage, and we're buying this storage, and we sort of do that. And then what we did instead was we spent $20 million, and we built a cryo facility to freeze samples, because it turns out storing stuff in the actual tissue or the DNA itself is a lot cheaper than buying storage. And so when you start thinking around that, you realize, of course, that DNA and RNA and cells themselves are, of course, a hard drive just as valid as anything you put in the computer. We also have data from humans, so photos of food, selfies, lots of cats, videos of people falling out of wheelchairs and tripping over things, and all sorts of fun and inappropriate things like that. Text and audio, that's really largely what we spit out as humans. You can basically guess the size of human-generated content. It's Google plus Facebook plus enterprise file and mail. That's the size of everything that we've generated, you know, is basically our human detritus that we're typically putting as either picture, video, text, or audio. We also now have data from machines, servers, phones, wearables, sensors, cars. You know, there's also sometimes this arbitrary definition of structured versus unstructured data, which I honestly don't like that term. It's more like, because all data, of course, has some structure to it. There's no like free-form data coming out of there. You basically have data where it's modeled, or you have data that's not modeled, you know, meaning you actually have a reproducible way that you can query it, or you got to figure some stuff out. And in fact, what you typically have, especially in the rise of machine data, is you have a lot of heterogeneous data. So data heterogeneity is the norm from now on. You won't be able to fit things in nice sort of bits. Now, if we actually start thinking around relative sort of data sets of this, and this is not drawn to scale because I wouldn't be able to fit humans, human-generated content's very small. If we actually decided that we're going to start even keeping event logs off of every thing that we've decided to put a chip into in some way, shape, or form, and even keep them around so you can do data mining or ad hoc analytics or start doing some more predictive things, the world of machine data is exceptionally large. And for those of you that are even now sort of sitting around and amazed that you have 2, 3, 4, 8, 10 petabytes of like web server log data, plus some other things, it becomes pretty sort of amazing. And then, of course, natural data is still huge, and we're never going to be able to do a lot of the fun, sciencey type things we want to do with it anyway. Now, data encoding, of course, is different for each. There's a physical representation for each. In the case of like, the stuff that we do in human data, in my opinion, the current one that we still know is the best is basically acid-free archival paper, right? So like, you can take a book and it instantly boots. You can read it at different sort of light levels. You know, it's like portable. And so, of course, you know, paper is still largely winning as far as a physical representation. Machine data, of course, is, well, it's from computers and it lives on computers, and it basically still is living in sort of a complex, whatchamacallit, atom, molecule, and so on. Then, of course, in the case of nature, it's things like DNA and RNA and the like. Now, data also only has 3 observers of it. There's only 3 things that observe data, and it turns out that it's also humans, machines, and nature. There's only sort of 3 students of data. Turns out it's also humans, machine, and nature. And so you can, in fact, say, well, you know, like 3 observers, 3 students, 3 this, 3 that. Then you just do 3 to the 3, and you basically come up with 27 sort of different little sort of possibilities. And I'll show you what I mean. What I mean is, what we've been doing is we've had humans learn after observing human source data. You have stuff that comes from nature, and nature learns. That's literally like a bacteriophage going in and infecting a bacteria and changing what it does. I mean, that's basically what that is. That's a data transmission. It's the organism learning and so on. Humans has also observed nature. We've used machines to observe natures, and then humans typically learn from it. Those last 2 bullets are typically sort of what we call science and so on. What's new, though, is we're basically taking human source data, machine source data, natural source, if you will, and we're using machines to observe them, and we're using machines to learn them. And so, in fact, the thing that's going on right now from a quote-unquote big data perspective is a machine data phenomena, in my opinion. Beyond everyone in the world taking videos of themselves doing something, you know, or, you know, again, my wife's the worst, for example. We go out and eat, and course comes out, takes a picture, course comes out, takes a picture, course comes out, takes a picture. I hate computers. So machine data, machine and human learning is sort of the big driver. And if you think about what it actually is driving, it's driving, and there's the magical synergy word called convergence, very synergistic. It's actually, that's supposed to not make sense, by the way. And so industry trends are pretty much when we decide that there's going to be a couple of our fundamentals converging on one another. And so one of those, for example, happens to be network. The other is compute, and the other is data. That's really literally all computers are. You got data, you do math, you send and receive it sort of over the network. We had things like the convergence of network and compute be formalized, and, you know, the good old slogan of the network is the computer, both the slogan for the PC and the internet cycle. We had compute and we had data and network convergence. That's the, hey, let's NFS mount this, and let's iSCSI block this, and we'll sort of do this, and we'll sort of do that, and we'll do all these sorts of things. And what you've noticed over the last couple of years, both in the sort of the rise of things like, if you remember the good old thumper out of Sun, to really what even the whole Hadoop sort of drive is right now and everything else, that's largely the convergence of compute and data. The idea that I have data, I store the data, and I'm literally going to go and do quote-unquote compute on it. And I'm going to do it in an arbitrary way. Like, I'm actually going to store heterogeneous data, and I'm going to do heterogeneous compute on it. I'm not going to store data in perfect little rows and just do SQL queries across that, do sort of different things. But I'm actually going to have heterogeneous data, heterogeneous compute, and that's going to be able to exist in like a platform, right? And so on. Now, of course, the other big trend is really around sort of also turning these things into centralized to decentralized to sort of distributed systems. And it's also somewhat of a little extra bit of data called metadata. So, of course, we also have data about data. And so really right now is like the rise of metadata and the importance of metadata. You know, like the similar thing where, well, you even look at a lot of stuff that's been in the news recently. You as a data source is not that interesting. What you do behaviorally and roam around the world might be. That's your metadata, right? When you even start looking at what you do in a storage system, there's even sort of the basic abilities to say, is my data unique or not? Like, you actually can't tell a file system, like, this data is unique, make sure it's actually in 12 data centers and never lose it, you file system and firmware and controller and sort of everything else like that. The other is, like, is my data important or not? And so, in fact, when we sort of sit down and say, just having basic, better metadata questions, like is it unique or not, is it sort of like important or not, start having some context in storage and data systems around like what data is and why we're sort of doing it and what we want to do with it. And then, of course, pulling all that metadata out so we actually can do distributed systems and the like. The other sort of simple thing is if you look at like what we do with data, all we do with data is we do math on it, we move it, we connect it, and we store it. In fact, when you look at the 4 functions, even in a data center, there's just a computer, a mover, a connector, and a store. So we might call them servers and routers and switches and storage, but you're basically just computing things, moving things, storing things, and connecting them. And we do just have the bit as our fundamental sort of like economic thing. It all rolls down to like a bit. And the ultimate representation, of course, is a bit as a single atom in a magnetic field pointing one direction or the other. That's like the quantum computer type thing. And we've seen them already. If you were a chemist and you ever did NMR, you basically were doing fundamentally the same sort of method. If you've had an MRI of your knee, you've basically done the same sort of fundamental method. An individual atom that, say, is odd numbered can wobble. When you put it in a magnetic field, it points with it or against it. Put a little energy in and it resonates to sort of the other side. And so, you know, how do you sort of sit down and take those types of systems and do that? Right now, of course, we're typically sort of encoding bits into sort of still, you know, electricity, and we're basically using, you know, fun little things in there. Bits per unit time is, in fact, our economic service. Like, it's always just everything. So the sad part is you basically weigh bits in bytes, and everything's bits per second, and pretty much every other sort of metric that you roll up anywhere inside computer science is some either bullshit metric that needs to be tossed through a wood chipper, or it's a derivative of one of these two things. Bits also live in containers, of course. On a disk, they live in blocks. In memory, they live in words. They live in registers. They live in things like packets on L3, which is sort of a PDU. And so everywhere in that sort of network compute and data part, we also then sort of have a container. And so the sort of abstraction of a container ship within there is pretty sort of valid. Now, the messed up thing about computers is we actually have no way to put metadata on bits themselves. Of course, they're only on containers, right? So you can't sort of ever track something like that, only sort of what it goes into. And when you start thinking around this whole sort of world of both the container ship and the pallet, physical sort of goods to digital goods, you start thinking around sort of the service provider business itself. It is fundamentally sort of best abstracted as a digital shipping and logistics business, right? And so you really start looking at things that way. The other thing that I think you will see show up right now, and we see this a bit in these sort of cloud providers and cloud space and everything else, is what will start rearing its ugly head, of course, is going to be risk, liability, and sort of insurance, right? And so in that, if what we're doing is, in fact, the new shipping, the new manufacturing, and the new sort of warehousing businesses, just like how AIG emerged as an insurance company in Shanghai to insure shipping lines, we're actually going to start having these issues show up even more in our industry. I mean, we very often sit down and say, well, we can't move something to a provider or a cloud or something because we can't get a contract or sort of do things like that. But what people are actually saying is that there's actually no insurer that I can go and get insurance to mitigate against business loss if something happens to that sort of data. And so just from a business perspective, expect the 400-year-old $4 trillion insurance industry to show up in the 50-year-old $2 trillion IT industry sometime soon. And I think it's going to be pretty interesting. The other thing, of course, that very often comes up is security and integrity. I basically define that as the prevention of corruption. That's security. Integrity is the detection of corruption. I go ahead and say that, like, just like how you can never actually prevent crime, you can never, of course, actually be secure, but you can decide, for example, that you can have data integrity. So you can, in fact, become perfect at catching criminals. And so recognizing that data integrity is as important as data security and sort of going through becomes a pretty close cousin, of course, around what you're doing from a risk and liability and insurance standpoint. And so the last little bit on that is really, of course, that I think what we're seeing from this data to the fact that we're warehousing data in these data centers, data centers now are becoming much more sort of like ports and factories, and we are in fact industrializing this whole thing. It means that once you sort of start doing that as a business, your business is a boring hardware supply chain business with a sort of tail and life cycle management. And it's largely because if you look at simple things like the delivery of a 4 gigabyte VM relative from 2009 to 2013, prices have actually been discounted, say, 83% over 4 years. Costs can be discounted sort of 94% in 4 years. And so unlike any sort of other industry in the world where, like, if this was a taxi industry and I was buying an automobile, this would be like buying a car, you know, literally say 4 years ago that got 32 miles a gallon for $20,000, and now I actually today bought a car that gets 640 miles a gallon, and I actually spent $300 on it. Like that's the ridiculous state that we've lived in sort of over the last 10 years. And it's really largely because the last 10 years has been a lot of change. The big change, of course, that showed up was that 64-bit x86 showed up. 64-bit x86 only turned 10 years old in April 2013. Of course, AMD shipped the first one in, you know, April 2003. Took Intel a little bit to sort of like catch up. Then, of course, from a virtualization standpoint, in the case of x86, unlike other chips, like, say, namely Power and Spark and the like, there were never even concepts of, say, virtualization in these chips as well. And so we also spent, say, with the launch of, you know, VMware Workstation 1.0 in 1999 all the way up to basically 2009. It wasn't until 2009 that even in x86, Intel finally shipped a chip and AMD shipped a chip that had both VTX and EPT in it. We could actually do full hardware-assisted virtualization. So that's only like 4 years old. Now, of course, with that, and the sort of irony is that x86 has won. And so current sort of chips are dead or dead men walking, or they're going to stay in a specialized sort of niche market. And even in the case of like ARM servers right now is just like this, like, hey, I've seen this show before. You know, you're like your 32-bit only and you don't have virtualization extensions in your ISA. So guess what? Thank you very much for making us do the same fucked up thing we did with x86 for a decade, which was largely sit around and come up with a bunch of sort of workarounds. So if you look at the chips, the funny part is we're also now down to three companies, Intel, Samsung, and TSMC, that do 90% of the world's fabbing. So of course x86 is all Intel. Samsung and TSMC do, in the case of TSMC, do some older Intel stuff, but that's basically where all the ARM servers are coming from. What's also happened over the last 10 years is the entire hard drive industry's collapsed into just Western Digital and Seagate. Those are the only two remaining hard drive makers. And if you actually look at 90% of the flash memory in the DRAM market, it's SanDisk, SK, Samsung, Toshiba, with Samsung and Toshiba being the real sort of monsters in that. And so it's really been sort of interesting when you start looking at this industrialization process and sort of data center as a big sort of factory type idea. What's also then happened in the component market is like, like it's just entirely sort of collapsed into like one dominant chip. You know, it's like Intel, Samsung, TSMC, that's it, right? It's two hard drive makers. It's basically down, it'll be down to two people making DRAM and most of the world's flash memory, and that's all. But then at the same time, what's happened for us on the developer and the sort of operations side, is applications. And so if we start thinking around what really started picking up as well was this, you know, we sort of, it's sort of awful, we call it Web 2.0, but you know, what it really was we decided that the main way that we were going to write an application over the last 10 years is the main way that we were going to access it was through a web browser instead of a custom client talking custom protocols, doing custom stuff. And we were actually going to have much more sort of distributed applications to do that. And so HTTP also won. You know, that of course has become really sort of the predominant way of writing applications today. And if you look at the fundamental point of any infrastructure, is just running apps and keeping data well. Like that's all it sort of is. If you look at like the desire typically right now and where the challenge is, what people want as defaults is they actually want scalable. That means scale down, scale up. They want geo-distributed. They want full transparency in their sort of applications. You know, that's what you want when you're running apps and you're sort of keeping data, but of course that's also exceptionally sort of challenging. What we've also seen over the last 10 years is the rise of the developer. That's really the global phenomenon. The fact of, and I say this all the time, like in the cloud space is CIOs and internal IT and very sort of often like that were not the people that showed up to use on-demand infrastructure. It's someone with an app that needs to run an app, that needs to get it out there, that sort of needs to do that. And what you see is I've seen really sort of this grassroots rise of the developer up. And then, of course, on the same sort of web bent, they're typically writing web apps, and then they became web apps that were service endpoints, that were API endpoints, that were then typically service or API endpoints behind a mobile application. And then, of course, as you start doing mobile and you start doing more devices and you start caring about what people are doing with the app and so on like that, you basically then have the rise of machine data out of those, and you have data services, and you sort of have that sort of the general sort of drive. The other one is that web scale has won. And so what I hate, honestly, when I sort of sit around with a good sort of say Fortune 50 CIO is like, well, like, can it really handle the scale of a company like this? And it's like, well, the bad news, and this of course was, the bad news of course for them is that Amazon, Microsoft, and Google are also Fortune hundreds now, right? So yes, in fact, someone like a Google has a larger app than you do. So yes, it sort of works and so on like that. And if you look at the way that I at least have always thought of cloud, is the cloud is operations as a service. Like if this is the one reason that you sort of go to a provider somewhere is to sit down and say, okay, well, I'm going to go to a provider and what they're actually going to give me is that scalable, geo-distributed, transparent by default. That what I want is, as it says there, a highly available, redundant, modular setup with a determinable quality of service, easy to administer, easy to sort of scale. You can right size it, which of course is sometimes a bad word, and you can sort of geographically distribute sort of without issue. And if you begin to start looking around like why people even consume stuff on computers and the like, then it's like, okay, well, I'm writing an app. I really sort of want the apps to behave in certain ways by default. I'm really sort of starting thinking about going to, say, someone, because what I'm really looking for is for them to help me operate the application. I'm trying to collapse the concept of, and we call it DevOps sometimes, but it doesn't really sort of quite even sort of capture it right. We're sort of collapsing this idea that the infrastructure gives you sort of a uniform type programmable interface across all the areas you care about, and you're really sort of getting ops as a service. The other sort of like two things that I sort of consistently bring up for this is if you look at like the other things that people want though, is not everyone actually wants scalable, geo-distributed, and transparent by default. Typically what I'll do is I'll divide these things up like performance, scalability, system comprehension, reliability, resiliency, security, integrity. You have things like agility, flexibility. You have stuff like ease of integration and so on like that. I tend to break, and this is pretty much if you go through the sort of list, it's pretty much like the 20 reasons why someone buys something that has to do with a computer. Like, oh, I'm using this service because it's very flexible, or I'm using this because it's high performance, or I'm using this because it's that, or I'm using it because it's very easy to integrate, or you have a pretty standard sort of set of terms on it. I typically break them up into sort of class 1, 2, 3 because that means that if you really care about a class 1 problem like performance, you'll give up class 2 issues and class 3 issues. As you guys know, if you're actually doing a high-frequency trading system and you care about performance, you don't give a rat's ass about flexibility or backward compatibility or sort of anything else like that. You're trying to drive these sorts of things. And so this is sort of a nice comprehensive reason. So we have to keep in mind that even though some people say come to quote unquote cloud and big data and the like for scalability reasons, there are actually some people that just care about ease of integration and flexibility as well. But if we start wrapping up a few of these modern challenges, and this is a slide that I borrowed from Brian Cantrell at one point, he came up with what I thought was a nice list of sort of these challenges across the network, compute, and data part. And they're really sort of grouped as density, observability, storage, and networking. And so a lot of it was like, well, could we think of sort of these easy one-liners where we sort of sat down and said, okay, well, like what's like all this SDN stuff? Like, well, what is it? You know, like what is it that everyone's sort of fundamentally trying to do? If you look at most of the density issues in the world are sort of like, well, how do you do high throughput real-time computing while basically still being highly dense? I mean, that's the challenge in most virtualization methods. How do you really sort of pile it on, have workloads line up, go pedal to the metal, except that it's very multi-tenant, very sort of dense. That's the challenge. If you look at the challenge around an observability standpoint, allowing sort of total transparency and real-time understanding of like latency outliers and the like is the real observability challenge. Storage, you actually want a single sort of storage abstraction that gives you both highly available, high latency, as well as low latency local stores. The entire sort of like SDN space is basically just giving each tenant their own orthogonal L2 and putting an L3 on each device and pulling the metadata out into something that's typically called a controller. It's not. Then everyone just picks in a different encapsulation method and what the controller is and those sorts of things. And then, of course, you know, from a freedom perspective, you actually want to be able to float between systems, and you actually want to start thinking very much along this idea that everything's actually been compromised and you sort of can't trust anything. And so your sort of security and integrity angle and the like becomes sort of big parts of those challenges. Now, a lot of, say, what we did in the Joyent world around density was a good combination of OS-level virtualization as well as hardware-assisted virtualization post-2009. Observability, which, of course, Brendan just got an award on basically his observability thing. That's like kernel statistics, DTrace, a lot of those sort of capabilities. Storage, as I'll show you in a bit, we did a very, you know, sort of simple design that was entirely dependent on ZFS. From a networking perspective, you can also now do full hardware-assisted virtualization in the networking stack as well, because modern NICs sort of support that. And all you basically need to do to sort of, you know, do something like this is decide that you're going to take a normal sort of thing that switches support like VLANs, and you're actually going to have them encapsulate something like VXLAN, and you're going to make a little piece of software that basically manages the signaling around that. It's not sort of like too much rocket science to do that. And so that's sort of a lot of the modern challenges in my opinion. And it's also this idea that we've been writing these applications, we've been sort of doing things from a you know, data perspective. And then what I've also seen happen over the last 10 years is I've seen the nature of applications change. And so applications now really sort of fit within this abstraction like world devices, network is the backplane type abstraction, meaning everything's a device. Data center's a device, phone's a device, the fridge is a device, the car's a device. It means that, you know, we're starting to head into things where data and connection intensive becomes the norm, real-time demands on something become the norm. When we start heading into things like real-time telemetry off of a pacemaker and a connected car, you know, driving by a busy baseball stadium where everyone's tweeting and Instagramming, and then all of a sudden your car's using the same mobile network and your pacemaker's using the same mobile network, having you basically blip out for 20 seconds and your car stop working is not okay. And so again, we're going to start having this thing where web scale and mobile and so on is going to move into this world of SCADA and fully industrialized type things. And that's basically going to be things where like stuff can't be dropped and there's actually a lot more connections and you're moving a lot of data. Message passing is currently sort of the thing that's won about how we do concurrency. That's sort of factual. And in fact, this idea that compute plus data really is sort of beginning to be a basic abstraction and a nice unified model. So again, if you start looking at even something like Hadoop as a data dumping ground and sort of having a nice programmable sort of interface, you know, so that you can write inside, you know, Java and so on, then when we start expanding that idea of like, okay, well, how do we start having storage platforms that take fully heterogeneous sort of data, but also do fully heterogeneous type compute? And I'll show you one of those types of platforms today. And then, of course, one of its chief architects is giving a talk on Friday, Mark Cabbage. It also means that if you start picking this apart, it meant that even within, say, the 10 years of sitting there at a system software company, that sort of transition from 32-bit to 64-bit and the sort of rise of density of systems and everything else, it meant that operating systems are not even remotely done. Runtimes are not even remotely done. And there's still a lot of innovation that needs to be done in the thing that runs bare metal. I mean, I'm sort of consistently shocked in that, you know, you can look at, say, the open source Smartos project, and you can look at a nice file there, and there's a bunch of updates in it, and the top line says copyright 1984 AT&T, and the bottom line says copyright 2012 Joyent. The fact that we actually had to, like, change a file there is amazing, you know, in sort of that. And so operating systems still have to be innovated on. Runtimes are still sort of important. And then, of course, if you can get to the point where you've written a bunch of middleware in the runtime that does unique things with the operating system, that starts being a fully sort of integrated stack. Now, if you start thinking around the data and the compute perspective, you know, we can take a single thing of data. Data here is represented by the orange ball. And then across a continuum to another bit of data represented by a blue ball. We can decide that we're going to have very simple sort of characteristics around data, like can you edit, can you append it? Can you make a change within a piece of data somewhere? Can you sort of change just the ends? There are, in fact, sort of things where you've decided that you can't edit, you can't append. There are things where you've decided that you can edit, you can append. And then, of course, there's append-only type sort of file system designs as well. Now, when you've decided that you can't edit, you can't append something, that's actually what we call an object in the file system world. And when we sit down and say that we call that a file. And I'm sorry to be very sort of basic on this, but a lot of times you say object and object storage, and people are like, well, I have a distributed object storage for my Java objects. And it's like, that's not the same object. I'm literally talking about just a good sort of solid bit. Now, if you start looking around, say, something like ZFS's design, ZFS is a local object store called the ZFS DMU, and then it actually has a POSIX-compliant file system layer on top of that. And then the way that those two talk to one another is a copy-on-write type semantic. So every time you sort of edit a file, there's, of course, a full copy, and then you get rid of the sort of original type thing. Now, what became interesting around the sort of base ZFS design is we could sit down and say, okay, well, what if we decided to enforce object semantics on some things, and we decided to allow file semantics on others? Then what it means is that the thing that you're doing on a file is typically persistent compute, where you're actually expecting that, say, virtual machine or database to read and write to that file system on nanosecond to microsecond type timescales. And it also means that the only way that you'll ever replicate it is synchronously. Like you're never, ever going to have that data in another data center that's connected by a normal network and expect it to actually always be exactly on time with one another. So can we actually sit down and have sort of a single ZFS layer expose sort of a block and bring that up with a file abstraction, allow sort of persistent compute, and then sort of have an ephemeral compute class as well. So sometimes we call it things like batch compute and non-batch compute. But this idea that you're typically just sort of doing compute where you're reading an object, you're doing something to it, you're writing a result down, and you're sort of doing that massively parallel. So one thing we decided to do at Joyent was to do sort of both compute services, but to actually go ahead and do sort of persistent compute on files and batch compute on objects. There's actually a lot of performance and price optimizations you can sort of do for both. But one way of thinking about it is like, well, what if you could basically run VMs and you could run containers directly on a SAN, right? So, and then on that, you're basically either telling it, yes, you can read and write to this as a file, or no, you can only read this as an object and you always have to write something else. But you sort of take this unified storage and compute, so rather than sort of taking the typical sort of SAN, pulling a LUN off, putting on a blade, running a VM on that, let's go ahead and have the same LUN living on a SAN, let's go ahead and have a VM running on top of that. Let's actually use asynchronous replication to sort of do tray-to-tray replication of that storage and even be able to move that VM around. But if we decide to enforce object semantics, then what we'll do is we'll actually do a strongly consistent multi-data center object store. But it's still one sort of platform. And so this idea of the unified storage model, where then compute just becomes a time-based policy. There's either compute that runs all the time or there's compute that doesn't. You sort of can easily divide it by the physics of the workload. And I'll show you in particular how on ZFS-based systems you can really cleanly demarcate all the different sort of workload classes that you sort of need to. Now, of course, this meant doing operating system work, we open sourced that a couple years ago, largely when we finished the KVM work, and so that's currently a project called Smartos. Smartos is a amalgamation, like imagine putting 3 different tasty things in your mouth, chewing it up, and then spitting it out type thing. It's got a kernel that started with Solaris 11 Nevada build 33, which of course started about 6 years ago. That's why ZFS is there. That's why DTrace is there. We needed a container abstraction. Originally when you started thinking about having had it over myself from using jails in the early days of FreeBSD to now sort of using zones inside of there. And then what the team at Joyent did as well was to actually do a complete KVM implementation there as well. And you actually have this weird operating system where it's like a Solaris kernel and a BSD user LAN and BSD device drivers and BSD libc, and then you have basically a full Linux toolchain in there as well. And so that's what I mean by an amalgamation. The design's pretty Unixy. Everything's a process, and so it's a pretty minimal kernel. I mean, the bootloader for Smartos is about 200 megabytes in size. It only net boots system. We actually don't install it on spindles. You basically lay down a ZFS object. You boot a container, so an OS level thing, the thing that is being rediscovered by parts of the Linux community right now. So you boot a container, and then you run a process inside of that container. And sometimes that process can be a native process, like it can be a JVM, it can be Postgres, it can be a Node.js process. But even if you look at Windows and Linux runs as a QEMU process inside of a container. And so as a result of that, you're able to do some nice sort of optimization. So because, say in the case of Windows, you put Windows inside of a, what's fundamentally a descendant of a Solaris container, and you wrap that inside a ZFS object. And what that means is you can take like a Windows image where as long as the working set size is smaller than the size of the image, and you can natively run that out of memory, basically, right? And also, it's pretty secure because the thing's inside of a container. And so from a operating system standpoint, and now I'm borrowing a couple slides from Brendan. Thank you, Brendan, for a couple slides. There's some design points and some advantages. We really decided to go after class 1 problems in Smartos, so really the performance, security, scalability, observability, reduced complexity, reliability problems. From a security perspective, as I said, it pixie boots an immutable platform image. So the one nice thing about Smartos is we decided that the operating system that runs bare metal should never be written to. So if you manage to get there, you're not installing a rootkit. You're not sort of doing anything like that at all. It also means we can timestamp it. We can do a number of things where we can verify the integrity of that image and so on. The ZFS devices themselves are also purely virtual. The fact that ZFS at the base within the DMU is an object store means that everything's transactional. There's always sort of an immutable object. Everything's got a checksum on at the end of the day. Resource controls are actually done at the layer of the container. There's no exploitable code paths to sort of modify privileges, and then we actually stuck KVM inside of an OS level virtualized thing. So we tend to sometimes call this double hold virtualization, mainly because double bagging your VM sort of failed the marketing test. It's true, actually. We'll double bag it. By the way, this gesture means I wasn't talking about a bag. And so the double hold virtualized stuff, you decide that you're going to take a zone, of course, completely de-escalate privileges inside of it, run KVM inside of there. Now, the very nature of hardware-assisted virtualization itself means you actually can sort of move back and forth. But the nice thing around OS-level virtualization is you can actually basically only have code paths that move in. So you do actually create sort of a positive pressure type containment there, and it's sort of pretty attractive. It also means that when you sort of combine OS-level virtualization, so containers and so on like that, with hardware-assisted, you also get, and this is also a nice slide from Brendan as well, so thank you again, Brendan. You also get some simplicity around I/O code paths and I/O code path optimizations. And so you literally basically then have a process that has, of course, access to a native driver than to hardware, rather than doing some of the typical gesticulations that you do in sort of other hypervisor designs. And so, we sort of started out saying, like, the truth is that if you don't care about operating system heterogeneity, which you honestly shouldn't if you are, like running all your own stuff, but once, you sort of do have to sort of care about it, then, thank God for, the Nehalem chip finally coming out. We were able to sort of sit down and do a highly minimized KVM implementation, but still sort of pull the network stack out below and still pull the storage part out below and so on like that. The scalability stuff means that, like, the speed of creating a zone is the speed of creating a ZFS device. That is actually, in fact, measured in the nanoseconds. There's no need for boot cycles on these. You have snapshots and clones, and so on like that. From an observability standpoint, there's a ton of providers inside of Smartos, and so it becomes, how do you truly observe internal behavior of guests? How do you observe guest-to-guest interactions? Providers and guests sort of observing the entire stacks. It uses DTrace and K-stats there pretty sort of extensively, it's nice. And then, of course, Smartos now is technically, effectively a distribution of the Illumos kernel project. And so, like Smartos and OmniOS and the Delphix and so on like that are some of the sort of predominant ones. Like, is Theo in the room? Oh, hey, there we go. Yeah, so that's the beautiful genius behind OmniOS. And so, if for some reason you're using Solaris still, stop and go find Theo, and he'll help you with your problem. So, yeah. Well, woo! Yeah, down with. I'm not going to say it. Unlike Cantrell's last USENIX talk, I'm not going to get edited. Okay. You know what I mean? There's going to be no disclaimer next to it, or so on like that. So that's a bit of the operating system stuff. The other sort of weird thing that we started doing at Joyent, like about 6 years ago, is we started like writing system software in JavaScript. that was another one. And then we spent like a really long time looking for ways to make that crappy, because if you've ever like ran JavaScript with something like Rhino several sort of years ago, it was like you sit there and you're like, why are we doing this? Why are we doing this again? Now, of course, the sad part as well is that, there's, of course, smatterings of like Haskell and Erlang and Perl and God knows what at one point as sort of experiments. But we did actually start doing a lot of things as well from a runtime perspective, and so that's a project we're pretty sort of heavily involved in called Node.js, which is typically referred to as a hipster douchebag runtime. That's true. That's true. It really is. It's got one of those, MongoDB and Node.js is web scale type sort of thing. So the funny part though is, because I don't always pay attention to what the cool kids are doing nowadays, and it's apparently become a very popular runtime now. We predominantly wrote stuff in C, and of course Node.js itself is in C and C++. Thank God for V8 coming out. Basically, I mean, if you look at what Node.js is, the Node part, as I tell you, is a thing called libuv, and it's combined with V8 from Google. Probably just a really sort of incredible language runtime from Lars Bakken team. We just needed like a dynamic C, and oddly enough, that became JavaScript. JavaScript, oddly, I just said oddly, like 20 times. Oddly, JavaScript's oddly very C syntax, oddly enough. And so it has a C-like syntax. It's actually a very light language. And so as you can imagine, when I'm sort of sitting there and saying like, oh my God, we're in the wilderness, we have to like go it alone, we're already doing like operating system work, we might have to do like runtime work, and we're writing all this middleware in the runtime, and my God, we might have to come up with a language. I really don't want to come up with a language. Can we not come up with a language? Can we please not come up with our own language? Because that's really douchey. In my like, you really, or Lucy. That's really not a good idea. And so JavaScript really ended up winning because of the C-like syntax or functional programming type languages, but then most importantly, JavaScript is not controlled by a single company. The spec is not controlled by a single company. It's actually part of EMCA or ECMA. Which one is it? ECMA, not EMCA. It's ECMA. Right? It's not a. Yeah. Okay. And so you could actually sit down and say, okay, well, there's a spec, and if we have to build our own VM, we can do that. And we don't have to come up with our own language for God's sake. And we began seeing Node essentially displacing C for core infrastructure software within Joyent. HTTP was clearly one of them, but we've actually now done DHCP servers in Node, DNS servers in Node, a full LDAP system, SNTP, HTTP proxies, a multi-data center key value store that lives on top of a distributed Postgres database. I mean, like a bunch of funny little things. The design points of Node, of course, is that it's just for servers talking a specific protocol. That's really what Node's for. Node's actually be an API endpoint, a service endpoint to do data ingress and egress. It is designed to be entirely cross-platform since 0.6. We did that with Microsoft. It is meant it actually only runs a single process on a single core on purpose. That's actually on purpose. It won't be multi-threaded. It'll never be multi-threaded. It won't be. We're going to run a process because what we decided as an abstraction at Joyent was just like that Smartos where I said we run a process inside of a container. Even our way of doing virtual machines is a process. And so we decided we were just going to run processes. That's what we were going to sort of do, and we're going to manage processes. Very Plan 90. Yeah, there's a lot of, since we also, of course, talked about that. The Node.js is actually a thing called libuv. If you actually try to do cross-platform asynchronous I/O across sort of Windows and Unisys, is Unisys actually plural for Unix? Is that? Yeah. Okay. Yeah. Why does that sound like I'm a Unisy? That's okay. Okay. I don't know. It's early, and I'm really I live on the West Coast, so. It's a C library that abstracts these two things, and people have combined it with other stuff, like Lua plus libuvs love it, which is, a couple, which is actually pretty funny and so on like that. And then, of course, one thing that was done by the team there as well was really to become somewhat obsessed with observability in Node.js. And so the one thing, despite being a cool hipster runtime that all the cool kids are using to do cool things now, like Node.js, level DB, you know what I mean? Mobile backends, all that stuff. It's actually the most observable language runtime as well. I mean, so we did quite a bit, around Node.js and Smartos in particular, around observability, instrumentation, and debugging, of course, in an interpreted language, which is normally sort of challenging. As it says there, of course, it gets more problematic in sort of large distributed systems, and so we did quite a bit around DTrace and MDB modules, and then a lot of the team, of course, worked on very sort of unique visualizations, ranging from heat maps to flame graphs, and of course, flame graphs was also a Brendan and Greg invention, because Brendan's really smart like that. So the questions of why is my app slow? Where's my Node program spending its time? Why is my memory usage growing steadily? Is it misconfigured? Is there a leak? Is there a problem with my app or the system? These are actually normally very intractable problems on a lot of systems. And so we decided to put things in place that would allow us to rapidly answer all four of these, and also allow other machines to even answer it and then make machine decisions for the machines, right? So, and so on. If you're not familiar with DTrace, this is a nice DTrace slide that I borrowed from Dave Pacheco. Don't guess, measure everything. Of course, DTrace is to do comprehensive tracing of both kernel and application level events. It does scale arbitrarily. It is suitable for production use. It has been open source now for 8 years. It's basically in everything but Linux right now, even though, of course, there is a little bit of a Linux. What's the Linux support that's currently for just system call provider and stuff like that? Okay, FPT, got it. And so you're able to sit down and do this sort of flame graph visualization where you say, from a CPU perspective, let's use DTrace and flame graph to sort of figure out where my time was spent in the application. able to do the same thing of DTrace and flame graphs with Node.js to sit down and say, how's my memory usage, sort of occurring. And then if you actually look at a thing called Node Panic, as well as if you're familiar with the modular debugger that was on Solaris, there's now a bunch of sort of modules inside MDB that we've put there where you can actually go to a running node process, dump core out of it, and then take that core into MDB and do like full post-mortem analysis of what was going on. And so, of course, this desire for us was the first two sort of DTrace-y type things as a process that's running all the time and say it's growing in memory, and you just want to know whether that's okay or not. What's key around post-mortem debugging of a dynamic language runtime is to sort of sit down and say, okay, well, now I'm going to walk up. This process is spinning at, say, 100%, and I need to actually, like, figure out what's going on. Normally, you never figure out what's going on. You basically go reboot the box is what you do. And so we worked pretty hard to sort of sit down and do a couple sort of very difficult things there. Dave Pacheco wrote a nice paper about it in ACMQ as well. It really sort of allowed us the ability to go and debug 1 in a billion type events. And so that was one sort of nice thing there. And so when we start thinking around this idea of data and data centers and new generations of applications and moving to the cloud to be sort of like operations as a service, and at the very least, as someone running a lot of infrastructure, we did decide to actually do like our own operating system work so we could innovate on that, largely so we could drive into the storage model, and started doing our own runtime work so that we could write a bunch of basic endpoints and middleware inside that sort of runtime. And if you start teasing this apart and you start thinking about, when you do your own infrastructure and you start writing your own distributed applications, what's sort of a basic service portfolio that you need, then what happens when you decide to build everything as sort of like a ZFS-based unified storage architecture is you can start having a relatively simple decision tree where you say, does my compute run all the time? And if it runs all the time, meaning you look over a 24-hour period and it's ran that entire period of time, then you're basically doing persistent compute on file. If it's not running all the time, then you're doing ephemeral compute on objects. And so you're really able to sit down and say, I can almost guarantee that anything that you're doing from a batch compute workload, ephemeral workload point of view, you're reading a bunch of data in and you're actually writing a bunch of new data. You're not overwriting the original data. You're not sitting there and doing something that's very sort of transactional. Those systems run all the time. And so what's nice around this sort of unified storage approach is you can cleanly sort of separate those workloads out. You can sit down and say, let's do persistent compute. Let's come up with names like standard and high CPU and high memory and high storage and high I/O. But the key thing really comes from the fact that because it's the unified storage design, because you're already sort of normalizing writes on like a flash device with ZFS, ZFS also has a very solid implementation of the ARC, so the adaptive replacement cache. So meaning you can actually sit down and say if you go and touch something on a disk, it will end up in memory. And ZFS will go and consume all available memory on the systems to sort of go and fill that up. It allows you to sit down and look at the amount of data you're dealing with and say, well, if your working set size fits in DRAM, is sort of like the first question. And so if it does fit in DRAM, then the very simple diagnostic is you'll see an ARC hit rate of like 90+%. And that allows you to sit down and say, okay, well now let's do a very standard workload then. A very standard workload is a 32-bit HPC workload. Meaning you've decided to basically put 10K SAS drives in there and it's 4 gigs of DRAM to 1 CPU. That's sort of the ratio. And then you can sit down and say, okay, well let's call high CPU a 1-to-1 ratio and let's call high memory a 1-to-8 ratio of DRAM to CPU. And you're able to now put together systems where you're shaping, sort of the number of hard drives and the amount of DRAM, but you basically have, one chassis, one board, same chip, and you're basically slotting in some different stuff. And you can have a rack of things that have a 1-to-1 ratio, a 1-to-3 ratio, a 1-to-4, a 1-to-5, a 1-to-7, a 1-to-8, a 1-to-16. And you can sort of easily sort of swap these components in, and you can make basically these different workload classes. And see, the beautiful part about this is since your working set size fits in DRAM, you'll actually get like DRAM type I/O performance when you use ZFS. The irony being is you can actually have like an 8 gig database and a 16 gig VM, come and run it on sort of a ZFS-based system, and it'll run faster than it will on SSDs because it's coming right out of memory, right? Now, if your working set size does not fit in DRAM, then diagnostically you see an arc hit rate that's decreased. Then the question becomes, do you care about IOPS? If you do care about IOPS, then the only way that you're basically going to restore that is by putting an array of SSDs in. So you use SSDs instead of SAS drives. If you don't care about IOPS, then you're basically not caring about the arc hit rate either. You come up with sort of quote-unquote high storage nodes, and you're typically using sort of 3 or now 4 terabyte nearline SAS drives. So things like we typically would use the Ultrastar 7K 4000, right? So the 4 terabyte Hitachi drives. Now, this is, if you look at like this sort of categorization, because of the approach of instead of taking a LUN off of storage and put it on a blade and run a VM on it, let's actually take storage where in the case of ZFS, there's things like the ARC, and there's the L2 ARC, and there's the ZIL. There's the ability to optimize I/O within that platform. And now what we can do is we can break things out into at least these 5. And like I said, in the case of high CPU and standard, you can do odd-numbered ratios depending on the type of app you're writing and the like. The only sort of workload class that's not here is basically big and fast. So what happens when you need like high storage and high I/O? Now, on a practical level, this means that you typically right now have an object or a file that's larger than 20 terabytes that cannot be subdivided in any sort of way, shape, or form, and you basically need like real-time scanning access to that. And so in that case, then by all means, you spend $1 million and you just put an array of Toshiba, like NAND inside of something. And so you do that. Now, then the fun part is, well, what happens if we're not running sort of a VM inside of a container that's reading and writing to sort of that ZFS object all the time? What if we decide instead that we're actually not going to run compute all the time? Then what you can do is you can actually use the same exact system to actually do an object store plus an ephemeral compute environment. And so what we did from an object store standpoint is sit down and say, okay, well, there's still the container that's there, but it's not always running. But we can actually use, say, the ZFS files and the ZFS DMU to sort of do a distributed object store. And so we also use the same exact storage layer to do a multi-data center object store that gives you sort of a granular copy policy. It is in kernel and sort of ZFS based, and so you can think of it as a cluster distributed version of ZFS, I guess. Compared to, say, other object stores like S3 and the like, those are typically written in an interpreted language like Java and living on top of normal sort of file systems. This sort of design allowed us to do some interesting things. The first one is we decided to make the object store strongly consistent on writes. And so if you put an object, subsequent get gives you the object. Highly available on reads, of course, and so it'll constantly sort of retry to get it from other locations. We believe this was actually the right choice for an object store, largely because it avoids client-side complexity and it gives you transparency, meaning a lot of the times you don't have to write an application where you fire off an object to a storage and then you say, are you there yet, are you there yet, are you there yet, are you there yet, are you there yet? If it's there, you get a 200. If it's not, you get a 404. If you can't write, you get a 503. And so the basic idea being if you're allowed to write and a 200's back, it will sort of do that. The added benefit of an object store of this design, of course, is that you can actually do an eventually consistent caching layer on top if you'd sort of like, because you can build eventually consistent on strongly consistent. You can't put strong on eventual and so on like that. Also, because of the ZFS part, there were some nice things, and it is an object store, but it does actually have Unix file system like semantics, so it has arbitrary namespaces effectively. You can pick whatever paths you want or the like. And then we actually use snapshots within ZFS objects to create something called snap links. And so meaning you can take all the objects, make snapshots of them that say have different names, but as long as you haven't written over the original object, those objects don't take up any additional space. And so you're able to sort of arbitrarily version sort of everything that you do. And again, a lot of that comes from having built on ZFS. The real advantage comes in the fact that there's still a container abstraction there. There's still an OS level virtualization that's there, right? So there's still a container. And then what it means is that the team built a file system that's in Smartos called HyperLofus. It's like a combination of temp and Lofus that allows you to take these ZFS objects and rapidly map them into containers, okay? And so as a result, you can do compute on objects, normal Unix-like semantics, map and reduce, or in the case of the Unix world, we call it split and cat. So you're able to sort of do those types of things. And it's a nice sort of key capability where you sit down and say, okay, well now you have sort of a complete batch compute environment without sort of any ETL and so on like that. And honestly, for me, you know, what was nice about this is this sort of was the final storage part where we sort of sat down and said, let's take ZFS and let's build both a very sort of high performance persistent compute offering, but also let's build a multi-data center object store that still allows you to do compute directly on the storage and so on like that. And so this became, you know, the sort of the holy grail we wanted to achieve, meaning a arbitrary storage environment that lets you store whatever you want and you can still do arbitrary compute on it. So it means, for example, that every object on the object store can be an executable for every other object. You write something in R, you upload it as a sort of thing, and then the API call that you make is take this R app and run it across my 1,000 objects, and so on like that. So then if you start thinking about the only thing that's basically left from a service offering standpoint is if you decide that you're going to go out and build a quote-unquote cloud or an infrastructure, being able to do persistent compute on file and ephemeral compute on object is actually the best demarcation for workloads. It allows you to sit down and really optimize what you're doing from a hardware perspective, a cost perspective. You have these clean things where you sit down and say, CPU bound over there, you know, high memory sort of over there. Anything batch goes directly on the storage. There's never sort of moving things around. You do need some basic traffic management, of course, but that's suited just fine. Typically what you build as well is a name service. So we're talking about typically a pub sub style name service that has exceptionally short TDLs. You know, typically a Paxos or now a Raft implementation that say is a consensus and durability as a service. And then you're typically from a data storage point of view doing a relational data service, a key value store, a directory service, and then sort of a larger directory service. At Joyent, for example, for a relational data store, we use Postgres. We actually use ZFS-based replication, so we actually use ZFS to replicate that around. The key value store is actually a layer that lives on top of that Postgres as well, and so does the directory service. And the directory is actually a thing called LDAP.js, and it's also open sourced. So in the final sort of bits here, I'd like to point out that if you decide that you want to do something like have your hair go gray, get sort of like really out of shape and do a lot of things, it is possible to spend about 8 years and build a complete, highly integrated system. Like you sort of have to do that. Now, the thing that I want to impart on everybody, though, from sort of some final things is if you look at general sort of career transformations, is I think that we're finally getting to the point now where we're not like putting together networks and we're not like doing VMs and stuff. We're in fact becoming exceptionally data-centric, and we're having to become very much scientists in our roles, meaning learn how to do experiments, you know, learn how to sort of sit down and do that, and really begin to experiment where most of what people are going to start doing is there's going to be a clean division of industries of people that like have data and use data to like make money, and then people that don't. And that will in fact transform every vertical, not just advertising like it currently has been, but it will start shaping manufacturing, telco, government, the whole sort of bit like that. And so making sure that, you know, one has real sort of data-centric capabilities. We're also moving from individuals, sort of servers and applications to systems. And so, you know, the one recommendation I have on that, of course, is study some statistics and learn things like R and start thinking around how we sort of do system science and the like. And then, of course, as a final thing, you know, over the years, you know, Jeff Bonwick, the creator of ZFS, has been a big inspiration on a number of things and always a phenomenal person to talk to. Cantrell, who was one of the guys that did ZFS, is great. Brendan, who, of course, just nicely won an award, was always a phenomenal colleague. Mark Cabbage, go see his talk on Friday. He'll actually talk about the in-depths behind Manta. Dave Pacheco really did a lot of that sort of innovative stuff around postmortem debuggability. Robert, Josh, you know, Mr. Mayo, Ben Rockwood, James Duncan, then of course is Isaac, who's the head of the Node.js project. Just a big, quick thanks for that. Thanks everyone for listening, and I'm available for questions, and of course, I'll be around all day. Thank you.
So if anyone has any questions, please head up to the microphone.
Mic it. Turn that mic on. Look at that.
There we go. Hi, I'm Rick Farrow. Nice talk. I liked it. Liked a lot of concepts, but I did have a sort of a quibble with one of them.
Okay.
You said you're going to PXE boot a very, very small, essentially kernel, but it's 200 megabytes. And to me, a very, very small kernel is something like SEL4, which comes from 10,000 lines of code.
I completely agree.
Okay.
Completely agree. It's just it's an operating system that's still smaller than a current Android update. So it's more of a criticism of
well,
it's more of a criticism of Google, you know, than
sure.
Than
No,
something else.
I certainly agree with you there. And Android has deservedly not so good
Yes.
security.
What I'll do from now on is I'll call it an appropriately sized for current times bootloader.
Okay. Thank you.
Thank you. Thank you. Completely agree. And see how nice that was because the puppy's there? Thank you. No, I got that from the internet.
So one of the things that I find kind of interesting is that we've gone through this long period of sort of boring commodity hardware. Mm-hmm. And we're coming out of this, particularly as data is becoming more important, into a time where there's going to be all sorts of kind of exotic components that are coming down the line. I mean, so we're starting to see a non-volatile storage. We'll probably start seeing things like smart memories in the next couple of years.
Yep.
How do you think these things are all going to figure into the system
architecture? Are we going to make a 64 to 128-bit transition? What happens when hard drives cap out at 24 terabytes? I mean,
right. So yeah, all of these hardware questions I think are pretty interesting because we're in some sense living in the end times, right? I mean, we're getting more and more cores, and you know, frequency scaling isn't really a big thing anymore. And
no, it's and I think that is and you know the. At one time it's disconcerting about the sort of, but the sort of, why am I only thinking deduplication as a word? But the deduplication in the component industry is it does take companies that can go and say allocate $10 to $12 billion a year in R&D to fix some of these. And if you look at a lot of the fundamental challenges around that, are material science issues. You know, can we actually get the materials to build sort of new things? You know, is there going to be a class of graphene-based something? As you know, I mean, so it's going to be exceptionally interesting. I mean, the last 10 years has been a fun run just because we sort of sat around with a bunch of one socket, 4 gig of DRAM, one CPU, x86 boxes, and then we had the little 64 core Sun thing in the corner, and and now. The idea that you're putting, it's just what you can buy, like what's in a $10,000 server today is amazing, relative to a few years ago. But yeah, at the same time, I think the thing is that it's only been what we've used to handle human-generated data and so on like that. If we're really going to go and achieve the things around this, whether you call it Internet of Things, whether you call it sort of like 50 billion mobile, like whatever you sort of want to call it. But if we actually want to start using computers to sort of impact human health and, our governments and, and what we're doing from, a wide range of utility industries and the like, it is going to require entirely different hardware. Which means, of course, we get to write yet another operating system. So. Yeah.
Hi.
Good morning.
So, sorry, I work in Google and we have a lot of Linux boxes. And my first week in work about 8 years ago, I was handed there's 15,000 broken boxes, SSH in and fix them.
Yeah.
Ever since then, I've decided that sysadmins, we need to get away from SSH. And looking at Smartos, I realized, the time has come where you never SSH into a box because there's too many of them. Seriously.
Oh yeah, absolutely.
Right. So, what can we do in the SmartOS world to get away, so get to a place where there is no SSH?
Well, I think it's more like, do we also get to a place where we effectively never do configuration management?
Well, certainly on the boxes.
And so, what you're effectively dealing with is essentially atomic platform images that have known configs, and you're basically sort of sitting there, and what you're actually doing is when you decide that you're going to push a change out to something, then usually what it is you're packaging up sort of a platform image, and then you put it up on the typical sort of image stuff, and then over some period of time you reboot 20,000 boxes, and now everything's been changed. So it is one of these potential things where we might be able to treat entire sort of operating system machine images as the unit that we decide to go out and change, and that's typically say what we would do.
So how are you going to sell that to a room full of people who are really good at SSH and all the commands you can run on the end of it?
I love it.
I'm not joking, guys.
I love SSH. I mean, even at Joyent, you had to use your SSH key to sign the API calls and the like. So, yeah, I mean. But
I'm trying to get to this idea that we use it for configuration at the moment because it's what we've always done.
Yeah.
And there's still configuration tweaking or even debugging, right? Even if you do have a good config system, you still might SSH in and attach GDB or DTrace or whatever. How do we get away from that so it's all completely distributed? And is that something you guys are interested in?
Yeah, but I don't have the answer to that. Sorry.
Okay, maybe next year.
Next time. New startup. Anything else? Well, that's it. Time's up. Thanks, everybody.